Ethanol stress corrosion cracking or SCC damage mechanisms as a part of environment-assisted cracking. Description of ethanol stress corrosion cracking or SCC damage mechanisms based on API 571, surface-initiated cracks caused by environmental cracking of carbon steel under the combined action of tensile stress and a fuel-grade ethanol, FGE, ASTM D4806, or FGE/gasoline blend environment. Dissolved oxygen and the presence of variable stresses such as cyclic stress or component flexing, increase the propensity for cracking. Here's a detailed description of ethanol stress corrosion cracking or SCC damage. Introduction. Stress corrosion cracking or SCC is a failure mechanism characterized by the growth of cracks in a material subjected to tensile stress in a corrosive environment. When this phenomenon occurs specifically in ethanol-containing environments, it is referred to as ethanol stress corrosion cracking. Ethanol SCC is a form of environmentally assisted cracking, where the combined effects of chemical environment, tensile stress, and microstructural susceptibility lead to crack initiation and propagation, often resulting in sudden and catastrophic failure of metallic components. Mechanisms of ethanol stress corrosion cracking or SCC damage includes, number 1 is environment and chemistry. Ethanol or C2H5OH is an alcohol that can be used as a fuel additive, solvent, or industrial chemical. Ethanol environments can be acidic, neutral, or alkaline, with the corrosivity influenced by impurities, temperature, and other environmental factors. Ethanol can decompose or react at high temperatures or in the presence of catalysts, producing reactive species such as acetaldehyde, acetic acid, or hydrogen, which can influence corrosion behavior. Mechanisms of ethanol SCC damage. Number 2 is material susceptibility. Materials vulnerable to ethanol SCC include certain carbon steels, stainless steels, aluminum alloys, and other high-strength alloys. Susceptibility depends on microstructure, alloy composition, heat treatment, and initial residual stresses. Mechanisms of ethanol SCC damage. Number 3 is crack initiation, initiated at microvoids, inclusions, microstructural heterogeneities, or pre-existing flaws. Localized corrosion or pitting at the surface can serve as initiation sites. Elevated tensile stresses or residual stresses facilitate crack nucleation. Mechanisms of ethanol SCC damage. Number 4 is crack propagation. Crack growth occurs via hydrogen-assisted cracking, film rupture, or intergranular attack. The environment affects film formation on the metal surface, includes, in some cases, passivating films, for example oxide layers, may form, but ethanol environments can disrupt these films. The cyclic formation and rupture of protective films create recurrent corrosion sites. Cracks tend to propagate intergranularly or transgranularly, depending on the material and environment. Mechanisms of ethanol SCC damage. Number 5 is fracture. The final fracture is brittle, often with cup and cone or intergranular features visible on fracture surfaces. The crack propagates rapidly once critical crack length is reached, resulting in sudden failure. Distinctive features of ethanol SCC includes environmental dependence. The presence of ethanol, especially at elevated temperatures, enhances susceptibility. Temperature sensitivity. Higher temperatures accelerate corrosion reactions and crack growth. Hydrogen involvement. Hydrogen generated during corrosion may diffuse into the metal, facilitating hydrogen embrittlement and crack growth. Microstructure effects. Materials with certain microstructures, such as coarse grains, inclusions, are more prone. Intergranular versus transgranular cracking. Intergranular SCC, cracks follow grain boundaries, often associated with corrosion products or segregation. Transgranular SCC, cracks pass through grains, often associated with embrittlement mechanisms. Factors influencing ethanol SCC includes, factor number 1 is temperature will impact to ethanol SCC when elevated temperatures increase chemical reaction rates, promoting SCC. Factor number 2 is ethanol purity and impurities will impact to ethanol SCC when impurities like water, acids, or other contaminants can increase corrosivity. Factor number 3 is stress level will impact to ethanol SCC when tensile stresses above a certain threshold promote crack initiation and growth. Factor number 4 is material microstructure will impact to ethanol SCC when grain size, inclusions, and phase distribution influence susceptibility. factor number 5 is environmental cycling will impact to ethanol SCC when fluctuations in environment, wet or dry cycles, can accelerate crack propagation. Detection and characterization method or technique of ethanol SCC damage includes visual inspection to detect surface cracks, corrosion pits and blistering, non-destructive testing, NDT, such as ultrasonic testing, detect internal cracks, eddy current testing, surface crack detection, radiography, internal flaw detection, replicate fractography, SEM analysis of fracture surfaces. Microstructural analysis includes optical microscopy to observe crack paths, SEM to analyze crack morphology and intergranular features, and chemical analysis test for corrosion products or localized chemistry changes. Preventive and mitigation strategies of ethanol SCC damage includes, the first is material selection. It is purpose to use corrosion-resistant alloys or materials with microstructures less susceptible. The second is environmental control. It is purpose to reduce ethanol temperature or limit ethanol exposure and remove impurities and control water content. The third is stress management. It is purpose to minimize residual stresses via heat treatments and design components to avoid stress concentrators. Preventive and mitigation strategies of ethanol SCC damage includes, the fourth is protective coatings. It is purpose to apply barrier coatings to prevent ethanol contact. The fifth is cathodic protection. It is purpose to use appropriate cathodic systems to suppress corrosion. The sixth is regular inspection and monitoring. It is purpose to employ NDT methods to detect early signs of cracking and use strain gauges or sensors for real-time stress monitoring. Ethanol stress corrosion cracking is a complex failure process involving the synergistic effects of chemical environment, tensile stresses, and material susceptibility. It typically manifests as intergranular or transgranular cracks that can grow rapidly once initiated, leading to sudden failure. Understanding the environmental conditions, microstructural factors, and stress state is vital for preventing and controlling ethanol SCC in critical components. Ethanol stress corrosion cracking affected materials based on API 571, number A, all grades of carbon steel are susceptible. Number B, ethanol SCC has not been reported in materials other than carbon steel, but general corrosion may be a concern with other materials including some alloys of aluminum, copper and copper alloys, lead and zinc. Number C, FGE and blends with gasoline may adversely affect non-metallic materials, for example coatings and seals, causing swelling, hardness changes, etc. Here's a detailed overview of materials affected by ethanol stress corrosion cracking or SCC. Ethanol SCC primarily impacts metals and alloys that are exposed to ethanol-containing environments under tensile stresses. The susceptibility varies based on the material's composition, microstructure, surface condition, and operational environment. Below is a comprehensive analysis of the key materials affected, along with their susceptibility and the factors influencing their vulnerability. Materials affected by ethanol stress corrosion cracking or SCC. Number 1 is carbon steels. Carbon steels widely used in pipelines, tanks, and structural components. It is composed mainly of iron with varying carbon content. Susceptibility of carbon steels includes, carbon steels are generally more susceptible to ethanol SCC, especially at elevated temperatures. Microstructural features such as grain boundaries, inclusions, and microvoids can act as initiation sites. Low alloying content and coarse microstructures increase vulnerability. Carbon steel's factors affected by ethanol SCC includes, higher tensile stresses, presence of residual stresses from welding or fabrication, impurities and alloying elements influence corrosion behavior. Materials affected by ethanol stress corrosion cracking or SCC. Number 2 is stainless steels, includes, number A, austenitic stainless steels, such as types 304, 316, generally resistant to many forms of SCC in aqueous environments, however, susceptible under specific conditions involving ethanol at elevated temperatures or in aggressive environments. Stainless steels. Number B, ferritic and martensitic stainless steels. More prone to SCC in ethanol environments due to their microstructural characteristics and lower corrosion resistance. Stainless steel susceptibility factors affected by ethanol stress corrosion cracking or SCC includes presence of chlorides or other halides can enhance SCC sensitization, chromium carbide precipitation at grain boundaries, increases intergranular attack, microstructural heterogeneities like inclusions or segregation. Materials affected by ethanol stress corrosion cracking or SCC. Number 3 is aluminum and aluminum alloys, generally less susceptible to ethanol SCC. However, high-strength aluminum alloys, especially those with intergranular precipitation or microstructural defects, may experience localized corrosion or cracking under stress in ethanol environments. Materials affected by ethanol stress corrosion cracking or SCC. Number 4 is copper and copper alloys, typically resistant to ethanol SCC. Notable exceptions involve high-stress conditions or impure ethanol environments, which can cause localized corrosion or cracking in certain circumstances. Materials affected by ethanol stress corrosion cracking or SCC. Number 5 is nickel and nickel alloys, such as Inconel, Monel. High corrosion resistance makes them less susceptible. Inconel alloys, such as Inconel 600 or 625, are often used in harsh environments, but susceptibility increases if microstructural heterogeneities or impurities exist. Materials affected by ethanol stress corrosion cracking or SCC. Number 6 is high-strength alloys and superalloys. High-strength steels and superalloys, such as Inconel, Hastelloy, may resist SCC in some environments but can become susceptible under high tensile stresses, especially at elevated temperatures. Materials affected by ethanol stress corrosion cracking or SCC. Number 7 is other metallic materials. Titanium and T alloys, generally resistant but can be affected under specific conditions, especially if contaminated or under high stress. Factors affecting material susceptibility to ethanol stress corrosion cracking includes grain size and inclusions. Finer grains often reduce susceptibility, inclusions increase SCC risk. Presence of impurities or segregations will impact to promotes localized attack or stress corrosion cracking. Heat treatment or microstructural stability susceptible to sensitization that will increases intergranular SCC risk. Elevated temperature and impurities increase susceptibility to ethanol stress. Corrosion cracking. Ethanol stress corrosion cracking affects a broad range of metallic materials, predominantly carbon steels and ferritic/martensitic stainless steels due to their microstructural susceptibility and environmental interactions. The material's microstructure, alloy composition, stress state, and environmental conditions collectively determine the degree of vulnerability. Material selection, microstructural control, stress management, and environmental control are vital for mitigating ethanol SCC risk in critical components. Ethanol stress corrosion cracking damage mechanisms. Critical factors based on API 571, Number A, several factors have been identified by field observations. Number 1, stress may be applied or residual. Highly stressed, locally cold worked components or components with stress concentrators are susceptible to cracking. Variable stresses, such as those produced by loading and unloading of tanks, have led to cracking in tank bottoms and floating roofs. Number 2, cracking has been found to occur in FGE meeting ASTM D4806 specifications, including the water content requirement. Number 3, corrosion inhibitors may be added to ethanol to prevent general corrosion in vehicle fuel systems, but their effect on SCC is not fully understood. Number B, other factors have been identified in controlled laboratory conditions using conservative slow strain rate test, SSRT, methods which stress the steel sample to failure. Evidence of SCC is based on the stress or strain behavior and an examination of the fracture surfaces. Number 1, aeration. For example, the dissolved oxygen content of the ethanol appears to be the most important factor for determining ethanol SCC susceptibility. Cracking has not been found under deaerated conditions. Number 2, the maximum potential for ethanol SCC occurs within a narrow range of water content between 0.1 and 4.5 vol%. Number 3, ethanol SCC has been found to occur in blends of FGE and gasoline containing as little as 20 vol% FGE. Number 4, galvanic coupling of a new steel to corroded steel increases the likelihood of ethanol SCC. Number 5, Increasing the chloride content of the ethanol tends to increase the severity of cracking and changes the crack type from mainly intergranular found in the field to transgranular cracking. Here's a comprehensive and detailed explanation of the critical factors that influence ethanol stress corrosion cracking or SCC damage. Ethanol SCC is a complex phenomenon governed by the interplay of environmental, material, and operational parameters. The critical factors are those conditions or properties that must be present or exceed certain thresholds to initiate and propagate SCC. Understanding these factors is essential for predicting, preventing, and controlling ethanol SCC damage. Critical factors influencing ethanol stress corrosion cracking or SCC includes, number 1 is environmental factors, includes, number A, ethanol composition and purity, ethanol concentration. Higher ethanol content generally increases the risk of SCC due to enhanced chemical reactivity and corrosivity, impurities, presence of water, acids, halides such as chlorides, or other contaminants can significantly increase corrosivity. Decomposition products, at elevated temperatures, ethanol can produce reactive species such as acetaldehyde, acetic acid, or hydrogen, which influence corrosion processes. Environmental factors. Number B is temperature. Elevated temperatures accelerate electrochemical reactions, diffusion of corrosive species, and microstructural changes. Higher temperatures can disrupt protective oxide films, making the metal surface more vulnerable. Threshold temperatures exist beyond which SCC susceptibility increases markedly. Environmental factors. Number C is pH and electrochemical conditions. Acidic or neutral environments tend to promote corrosion. Changes in pH can alter passivity and film stability on metal surfaces. The presence of chlorides or halides can break down passive films and promote localized attack. Environmental factors. Number D is cyclic environmental conditions. Fluctuations between wet and dry states can cause repetitive film formation and rupture, promoting crack initiation and growth. Temperature cycling can induce thermal stresses that synergize with chemical attack. Critical factors influencing ethanol stress corrosion cracking or SCC. Number 2 is material factors, includes, number A, microstructure of the material, grain size. Coarser grains often have higher susceptibility due to larger grain boundary area. Inclusions and segregations. Non-metallic inclusions or segregated impurities act as initiation sites. Heat treatment state. Sensitized microstructures with chromium carbide precipitation at grain boundaries are more vulnerable. Material factors. Number B is mechanical stress state, tensile stresses. Both residual stresses, from welding, machining, and operational stresses can exceed the material's threshold, facilitating crack initiation. Stress concentrators, notches, welds, corrosion pits, or surface defects amplify local stress levels. Stress intensity factor. K. The applied stress must surpass a critical value for crack propagation. Material factors. Number C is residual and operational stresses. Residual stresses from manufacturing or welding can predispose components to SCC. Operational stresses, such as pressure or mechanical loads, can reach critical levels. Material factors. Number D is material susceptibility. Alloy composition, microstructural stability, and surface condition influence vulnerability. High-strength alloys often have higher susceptibility due to their susceptibility to embrittlement under corrosive conditions. Critical factors influencing ethanol stress corrosion cracking or SCC. Number 3 is environmental material interaction factors, includes, number A, protective film formation and stability, passivity, formation of oxide or film layers that protect the surface, film breakdown. Ethanol environments can disrupt or prevent stable passive film formation, repassivation rate. The ability of the material to reform protective films after rupture influences SCC susceptibility. Environmental material interaction factors. Number B is hydrogen embrittlement. Corrosion processes generate hydrogen atoms that can diffuse into the metal. Hydrogen can reduce ductility and promote crack initiation and propagation. Environmental material interaction factors. Number C is localized corrosion and pitting. Micropits or corrosion sites serve as crack initiation points. The size and distribution of pits influence the local stress concentration. Critical factors influencing ethanol stress corrosion cracking or SCC. Number 4 is operational and design factors, includes, number A, stress level and distribution. Stresses exceeding the material's threshold are critical. stress concentration factors from design features, such as welds, bends, increase SCC risk. Operational and design factors. Number B is component geometry. Sharp corners, welds, and surface irregularities serve as initiation sites. Thinner sections are more prone to crack propagation. Operational and design factors. Number C is operating conditions. Flow velocity. High flow can remove corrosion products and disrupt passivation. Cycle times. Repeated environmental changes promote crack growth. Maintenance and inspection. Lack of early detection facilitates progression of SCC. Critical factors influencing ethanol stress corrosion cracking or SCC. Number 5 is threshold and critical conditions. Critical stress intensity factor, the minimum stress intensity required for SCC crack growth. Critical environment composition, a threshold ethanol purity, impurity level, or temperature that must be exceeded for SCC to occur. Time to crack initiation, the time required for microcracks to form under given conditions. The critical factors for ethanol SCC damage are those that create a conducive environment for crack initiation and provide the necessary stresses and microstructural vulnerabilities for crack growth. These include elevated temperature, tensile stresses surpassing threshold levels, microstructural features, presence of impurities, and disruption of protective films. Effective mitigation involves controlling these factors, such as reducing residual stresses, selecting resistant materials, maintaining favorable environmental conditions, and implementing appropriate inspection regimes. Ethanol stress corrosion cracking damage affected units or equipment based on API 571, Number A, carbon steel storage tanks, rack piping, and associated equipment are susceptible to ethanol SCC. All grades of carbon steel are susceptible. Number B, cracking has also been reported in a pipeline used to transport FGE to and from a terminal. Number C, ethanol SCC has not been reported in FGE manufacturers' equipment and tankage, or in transportation equipment, barges, trucks, railcars. Number D, cracking has not been reported in equipment handling FGE after it has been blended with gasoline at end-use concentrations in unleaded gasoline, 10 vol%. There has been one reported failure of an end-user E85 tank. Here's a detailed overview of units and equipment affected by ethanol stress corrosion cracking, SCC, including explanations of how and where these damages typically occur. Ethanol SCC primarily impacts metallic components exposed to ethanol-rich environments under tensile stress. Various industrial units and equipment types are susceptible depending on operational conditions, materials used, and environmental exposure. Affected units and equipment by ethanol stress corrosion cracking includes, number 1 is pipelines and storage systems, includes transport of ethanol and ethanol-containing fuels. Widely used in oil, gas, fuel distribution, and chemical industries. Pipelines and storage systems. Susceptible locations includes welded joints and heat-affected zones. HAZ microstructural heterogeneities make these areas vulnerable. Bends, elbows, and T's, locations with high stress concentration, thin sections or corrosion pits, microdefects that can initiate cracking. Pipelines and storage systems. Damage manifestation includes longitudinal or transverse cracks starting at welds or defect sites, propagation leading to leaks, ruptures, or catastrophic failures. Affected units and equipment by ethanol stress corrosion cracking. Number 2 is storage tanks and vessels, includes tanks storing ethanol, ethanol blends, or ethanol-based fuels, chemical reactors or processing vessels handling ethanol streams. Storage tanks and vessels. Susceptible locations includes welded seams and nozzles, corrosion-prone areas with residual stresses, corrosion pits or microcracks at the bottom or sides. Storage tanks and vessels. Damage manifestation includes cracks propagating from weld defects or corrosion sites, potential for sudden leaks or structural failure, especially under internal pressure. Affected units and equipment by ethanol stress corrosion cracking. Number 3 is heat exchangers, includes devices exchanging heat between ethanol-containing fluids and other process streams. Components include tubes, shells, headers, and welds. Heat exchangers. Susceptible locations includes tube-to-header welds, bends and expansion joints, areas with localized stress or temperature gradients. Heat exchangers damage manifestation includes cracks initiating at welds or stress concentrators, reduced heat transfer efficiency, risk of fluid leakage. Affected units and equipment by ethanol stress corrosion cracking. Number 4 is valves and fittings, includes control devices regulating fluid flow in ethanol handling systems, includes ball valves, gate valves, check valves, and fittings. Valves and fittings susceptible locations, includes seals, seats, and weld joints, areas with high operational stresses or vibration. Valves and fittings damage manifestation includes crack initiation at welds or stress points, leakage or failure of valve components, affecting process safety. Affected units and equipment by ethanol stress corrosion cracking. Number 5 is pumps and compressors, includes mechanical equipment moving ethanol or ethanol mixtures, critical in fuel dispensers, processing plants, and transportation units. Pumps and compressors susceptible locations, includes shaft welds and coupling points, impeller blades and casing welds, bearings and stress concentration points. Pumps and compressors damage manifestation includes cracks that compromise pump integrity, leading to leaks or failure, possible catastrophic breakdowns if cracking propagates unnoticed. Affected units and equipment by ethanol stress corrosion cracking. Number 6 is storage and transport containers, includes tanks, drums, or containers used for storing ethanol or ethanol blends, often constructed from carbon steel, stainless steel, or alloys. Storage and transport containers susceptible locations, includes welded joints, seams, and closures, microstructural features susceptible to SCC. Storage and transport containers damage manifestation includes initiation of cracks at weld defects, leading to leaks or rupture, environmental contamination and safety hazards. Affected units and equipment by ethanol stress corrosion cracking. Number 7 is process equipment in chemical and fuel industries, includes reactors, mixers, separators, and other process units handling ethanol streams. Process equipment in chemical and fuel industries susceptible locations, includes welded joints, microvoids, or areas with residual stresses. Equipment with temperature fluctuations or cyclic stresses. Process equipment in chemical and fuel industries damage manifestation includes cracks reducing structural integrity, risking process leaks or shutdowns. Operational and safety implications includes leakage and environmental contamination. Cracks can lead to ethanol leaks, posing fire, health, and environmental hazards. Structural integrity. Progressive cracking undermines the strength of tanks, pipelines, and vessels. Operational downtime. Equipment failure due to SCC necessitates repairs, replacements, and shutdowns. Safety risks. Catastrophic failures may cause injuries, fires, or explosions, especially in flammable ethanol environments. Ethanol SCC affects a broad range of industrial units and equipment, especially those with welded joints, residual stresses, and microstructural vulnerabilities. The most vulnerable locations include welded seams, bends, corrosion pits, and stress concentration zones. Early detection, material selection, and proper maintenance are critical to prevent damage and ensure safe operation. Ethanol stress corrosion cracking appearance or morphology of damage based on API 571. Number A, ethanol SCC is often found in the vicinity of welds and can appear as cracks that are parallel to the weld or transverse to the weld. See Figure 4-162, ethanol SCC in steel tank bottom. Note crack running parallel to fillet weld and striker plate. See Figure 4-163, ethanol SCC in a steel air eliminator vessel. Note cracks running perpendicular to the weld. See Figure 4-164, a leak in piping resulting from an ethanol SCC adjacent to the weld. See Figure 4-165, SCC in steel pipe from a loading rack supply line. The top figure shows a 7-inch long crack parallel to the weld root on the pipe ID surface. The bottom picture is a cross-section of above crack showing initiation outside the weld heat affected zone on the pipe's inside surface, nidal etch. See Figure 4-166, SCC of steel piping in a fuel ethanol system return line/tank transfer line. The top picture shows the crack parallels the pipe to T circumferential weld. The bottom picture shows the inside and outside of the pipe after splitting and cleaning the weld area. Parallel SCC cracks are clearly visible adjacent to the weld. See Figure 4-167, the top picture shows cracking initiating in the base metal on the ID of a section of piping adjacent to the weld. The bottom picture is a high magnification photomicrograph of the crack above illustrating the predominantly intergranular nature of the cracking. 380x, Nidal etch. See Figure 4-168, transverse cross-section of a piping section exposed to fuel ethanol showing multiple crack initiation sites characteristics of SCC. See Figure 4-169, photomicrograph of SCC in a steel tank bottom showing highly branched, intergranular cracks at 100x. Number B, cracks are typically tight and may be filled with corrosion product. Number C, ethanol SCC cracks are typically branched and intergranular, but transgranular or mixed mode cracking has also been reported. Field failures tend to be intergranular, while laboratory testing has produced all crack morphologies. The cracking mode appears to depend on the chloride level, with an increased chloride content tending to shift the cracking from intergranular to transgranular or mixed mode. Number D, microstructure of materials subjected to ethanol SCC are typically ferrite, or ferrite and perlite. Here's a detailed explanation of the appearance and morphology of ethanol stress corrosion cracking, SCC, damage. The morphology of SCC damage refers to the visual and microstructural features that characterize cracks and related corrosion phenomena caused by the synergistic action of tensile stresses and corrosive ethanol environments. Understanding these features is crucial for damage identification, failure analysis, and preventive measures. Appearance and morphology of ethanol stress corrosion cracking damage includes: number 1 is macroscopic appearance, includes: number A, fracture surface features. They are such as ductile and brittle appearance. Ethanol SCC often exhibits a brittle fracture morphology, characterized by a rough, faceted surface with features resembling intergranular or transgranular cracks. In some cases, especially under lower stress or in less susceptible microstructures, the fracture may appear mixed mode. Combining features of ductile and brittle failure. Macroscopic appearance. Number B is visible cracks, includes: longitudinal cracks. Cracks often run parallel to the stress direction, especially in pipelines and welds. Localized pitting or microcracks. Microscale pits or corrosion sites may be visible, often at welds or inclusions. Pattern of crack propagation. Cracks may display intergranular, along grain boundaries, or transgranular, through grains, paths. Macroscopic appearance. Number C is surface features, includes: rough, granular, or faceted surfaces, indicative of brittle fracture modes, step-like features, resulting from crack propagation across microstructural features. Appearance and morphology of ethanol stress corrosion cracking damage. Number 2 is microstructural morphology, includes: number A, crack path and mode, includes: the first is intergranular SCC, cracks propagate along grain boundaries, often appearing as branching or network-like features. Grain boundary attack leads to widened, flattened, or scalloped features. The second of crack path and mode is transgranular SCC, cracks cut through grains, often along slip planes or microstructural weaknesses, exhibits cleavage facets and striations indicating cyclic or stepwise crack growth. Appearance and morphology of ethanol stress corrosion cracking damage. Number B of microstructural morphology is microcracks and pits. Microcracks is the small cracks within the microstructure, often less than a few micrometers in length. Microcracks can coalesce to form larger cracks. Corrosion pits is the microvoids or pitting corrosion sites often act as crack initiation points. Pits are typically rounded or irregular and may be associated with inclusions or impurities. Number B of microstructural morphology is microstructural features, includes: decalcification or carbide precipitation, microstructural changes near cracks, such as chromium carbide precipitates at grain boundaries, sensitization, facilitate intergranular SCC, inclusions. Non-metallic inclusions act as stress concentrators and initiation sites for cracks. Appearance and morphology of ethanol stress corrosion cracking damage. Number 3 is fractography features, includes: number A, faceted fracture surfaces that is intergranular facets appears such as flat, smooth surfaces along grain boundaries. Indicate brittle intergranular cracking typical of SCC. Number B of fractography features is step-like or terraced morphology. Cracks may show stepwise propagation, especially in transgranular SCC. These steps are often associated with microstructural barriers like grain boundaries or precipitates. Number C of fractography features is secondary features, includes hackle marks, fine striations or lines indicating crack growth direction, and beach marks or striae, indicate cyclic loading or environmental fluctuations during crack growth. Number 4 of the appearance and morphology of ethanol stress corrosion cracking damage is microstructural cross-section features, includes crack tip morphology, often exhibits microvoid coalescence or cleavage facets, widened grain boundaries. Due to corrosion attack, grain boundaries appear wider and more irregular, localized corrosion zones, areas with discoloration, corrosion products, or oxide layers. Number 5 of the appearance and morphology of ethanol stress corrosion cracking damage is corrosion products and deposits, includes oxide or acetate layers, may form on fracture surfaces, slightly obscuring morphology, hydrogen-induced blisters or cracks. Underlying microstructural damage may be associated with hydrogen embrittlement features. The appearance and morphology of ethanol SCC damage are characterized by brittle fracture features, intergranular or transgranular cracks, and microstructural evidence of corrosion attack, such as pits and widened grain boundaries. These features are critical for damage assessment and failure analysis in ethanol handling equipment. Ethanol stress corrosion cracking damage prevention and mitigation based on API 571, Number A, the likelihood of ethanol SCC can be reduced through PWHT, when possible, or by applying coatings. Given the high threshold stress intensities required to initiate ethanol SCC, standard carbon steel PWHT is expected to be effective. Research to confirm this is currently underway. Number B, avoid designs with highly localized tensile stresses. Number C, avoid the usage of lap seam welds that may concentrate strain in components. Number D, minimize cold working during fabrication. Here's a comprehensive, detailed overview of prevention and mitigation strategies for ethanol stress corrosion cracking. These measures aim to reduce the risk of crack initiation and propagation, ensuring safer operation of ethanol-containing systems. Effective management of ethanol SCC involves a combination of material selection, design practices, operational controls, and inspection techniques. Below is an in-depth discussion of each category. Prevention and mitigation of ethanol stress corrosion cracking damage includes, number 1 is material selection, includes, number A, use of SCC-resistant materials. The first is using corrosion-resistant alloys, includes, stainless steels, for example 304L, 316L, 321, 347, with low carbon content to minimize carbide precipitation. Nickel-based alloys, for example Inconel, Monel, for highly aggressive environments. The second is using high-performance plastics and composites, for non-metallic components, if applicable, though limited in load-bearing applications. Number B of material selection is microstructure control, includes, minimize sensitization, use low-carbon steels or stabilized grades to prevent carbide precipitation at grain boundaries, and homogeneous microstructures, ensure minimal inclusions, microvoids, or residual stresses during manufacturing. Prevention and mitigation of ethanol stress corrosion cracking damage. Number 2 is design considerations, includes, number A, stress reduction, includes, eliminate or minimize residual stresses, proper welding procedures, post-weld heat treatments, and stress relief annealing, design for stress distribution, avoid abrupt changes in cross-section, sharp bends, or stress concentrators, use of smooth transitions. Incorporate gradual geometrical changes to reduce localized stress. Number of design considerations is avoidance of microstructural discontinuities, proper welding techniques to prevent microcracks and inclusions, designed to minimize crevices, entrapments, or stagnant zones where ethanol may concentrate. Prevention and mitigation of ethanol stress corrosion cracking damage. Number 3 is environmental control, includes, number A, control of ethanol composition, includes, limit ethanol concentration, lower ethanol content if feasible, as higher concentrations tend to increase SCC susceptibility, reduce water content, minimize moisture levels that can facilitate corrosion processes. Number B of environmental control is control of operating conditions, includes temperature management, keep operating temperatures below critical thresholds where SCC accelerates, avoid cyclic stresses and fluctuations, reduce cyclic loading or thermal fluctuations that promote crack initiation. Number C of environmental control is use of inhibitors. Application of corrosion inhibitors compatible with ethanol systems to suppress corrosion reactions. Prevention and mitigation of ethanol stress corrosion cracking damage. Number 4 is protective coatings and barriers, includes, number A is coatings. The first coating is organic coatings, epoxy or polyurethane coatings to isolate metal surfaces from ethanol exposure. The second coating is metallic coatings, cladding or overlays of corrosion-resistant materials. Number B of protective coatings and barriers is linings in tanks and pipelines. It is use of compatible linings to prevent direct contact between ethanol and susceptible metals. Prevention and mitigation of ethanol stress corrosion cracking damage. Number 5 is cathodic protection. Application of cathodic protection systems, e.g., sacrificial anodes or impressed current, to reduce electrochemical potential and inhibit corrosion processes. Prevention and mitigation of ethanol stress corrosion cracking damage. Number 6 is maintenance and operational practices, includes, number A, regular inspection and monitoring, including the following methods. The first method is non-destructive evaluation or NDE, ultrasonic testing, radiography, dye penetrant, and eddy current inspections to detect early cracks or corrosion. The second method is visual inspections, frequent surface checks for signs of discoloration, pitting, or microcracks. Number B of maintenance and operational practices is cleaning procedures, prevent buildup of contaminants that could initiate localized corrosion, use compatible cleaning agents that do not damage protective coatings. Number C of maintenance and operational practices is leak prevention, ensure integrity of welds, seals, and joints to prevent ethanol leakage and ingress of moisture. Prevention and mitigation of ethanol stress corrosion cracking damage. Number 7 is operational strategies, includes, number A, stress management, limit operational stresses through controlled startup/shutdown procedures, avoid sudden pressure surges or mechanical shocks. Number B of operational strategies is temperature and humidity control, maintain stable temperatures and humidity levels to prevent environmental fluctuations that could promote SCC. Number C of operational strategies is process optimization, optimize flow rates to minimize stagnant zones, avoid conditions conducive to microcrack initiation. Prevention and mitigation of ethanol stress corrosion cracking damage. Number 8 is training and personnel awareness, educate operators and maintenance personnel about ethanol SCC risks, implement procedures for early detection and response. Preventing ethanol SCC is a multifaceted approach that combines appropriate material selection, sound design, environmental controls, protective coatings, and vigilant maintenance. Proper implementation of these strategies significantly reduces the risk of crack initiation and growth, ensuring the safety and integrity of ethanol handling systems. Ethanol stress corrosion cracking damage inspection and monitoring based on API 571. Number A, it is difficult to visually detect ethanol SCC because the cracks are typically tight and filled with corrosion product. Some small leaks may occur before an ethanol crack can be visually detected. Number B, WFMT is the preferred method for detecting ethanol cracking. Methods for ethanol SCC inspection are similar to those used for detecting other types of SCC. Number C, shear wave UT may be used in instances where WFMT is not feasible. Number D, ACFM can be used with less surface preparation than WFMT in areas such as weld HAZs. Number E, EC is unproven as a method for detection of ethanol SCC. Here's a comprehensive, detailed overview of inspection and monitoring methods used to detect ethanol stress corrosion cracking, SCC, damage. These techniques are essential for early detection, preventing catastrophic failure, and ensuring the integrity of ethanol-containing systems. Inspection and monitoring methods for detecting ethanol stress corrosion cracking damage. Number 1 is visual inspection. This is the most fundamental and straightforward method. Performed with the naked eye or with magnification tools, such as magnifying glasses, borescopes. Application visual inspection is surface examination of accessible areas such as external surfaces, welds, and joints. Look for discoloration, corrosion pits, cracks, or blistering. Use borescopes for internal inspection of pipelines, tanks, and vessels. The advantages of visual inspection is cost-effective. Immediate feedback. Useful for identifying gross damage, corrosion products, or surface cracks. The limitation of visual inspection is, cannot detect subsurface or micro cracks, limited effectiveness in opaque or coated surfaces. Number 2 of inspection and monitoring methods for detecting ethanol stress corrosion cracking damage is non-destructive testing or NDT techniques, includes NDT techniques. Number A is ultrasonic testing or UT. Principle of UT uses high-frequency sound waves transmitted into the material. Cracks or flaws reflect the sound waves, which are detected and analyzed. Application of UT is to detect internal cracks or thickness loss due to SCC, suitable for pipelines, vessels, and welds. Types of UT includes pulse-echo method, detects reflections from flaws. Phased array ultrasonic testing or PUT, provides detailed imaging. The advantages of UT: it can locate subsurface cracks. It is a quantitative measurement of crack depth and size. The limitations of UT includes, requires skilled operators. UT difficult to perform in complex geometries or rough surfaces. Number B of NDT techniques is radiography testing or RT. Principle of radiographic testing: it uses X-rays or gamma rays to produce images of internal features. Application of radiographic testing is to detect internal cracks, voids, or corrosion-induced thinning. The advantages of radiographic testing is, provides detailed images of internal defects. Non-contact method suitable for multiple materials. The limitations: radiographic testing is, safety concerns due to radiation, less effective for very small cracks. Number C of NDT techniques is magnetic particle testing or MT. Principle of magnetic particle testing is detect surface and near-surface cracks in ferromagnetic materials by applying a magnetic field and iron particles. Application of magnetic particle testing is surface crack detection, especially near welds and stress concentration zones. The advantages of magnetic particle testing is, sensitive to small surface cracks, rapid and portable. The limitations: magnetic particle testing is, only applicable to ferromagnetic metals, cannot detect subsurface cracks. Number D of NDT techniques is penetrant testing or PT. Principle of penetrant testing is uses dye penetrants applied to the surface to reveal surface-breaking cracks. Application of penetrant testing is to detect surface cracks, especially in welds or areas with complex geometries. The advantages of penetrant testing is, simple and inexpensive, effective for surface cracks. The limitations of penetrant testing is, cannot detect subsurface cracks, surface must be clean and dry. Number E of NDT techniques is eddy current testing or ET. Principle of eddy current testing is uses electromagnetic induction to detect surface and near-surface flaws. Application of eddy current testing is suitable for detecting cracks in conductive materials, especially in complex geometries. The advantages of eddy current testing is, sensitive to surface and subsurface flaws, rapid testing. The limitations of eddy current testing is, limited penetration depth, requires calibration for specific materials. Here's the advanced NDT and inspection techniques, includes, number A, acoustic emission or AE monitoring. Principle of acoustic emission is to detect transient elastic waves generated by crack growth or microstructural changes. Application of acoustic emission is continuous real-time monitoring for crack initiation and propagation during operation. The advantages of acoustic emission is early detection of active crack growth and suitable for in-service monitoring. Number B of advanced NDT and inspection techniques is digital radiography and computed tomography or CT. CT provide high-resolution 3D imaging of internal defects. Number C of advanced NDT and inspection techniques is guided wave ultrasonics. It is suitable for inspecting long pipelines from a single access point. Number 4 of the inspection and monitoring methods for detecting ethanol stress corrosion cracking damage is monitoring techniques for early detection, includes, number A, strain gauges and stress monitoring. Install strain gauges on critical components to detect abnormal strain accumulation. It is helppful for assessing stress levels that may promote SCC. Monitoring techniques. Number B, corrosion rate monitoring. Use linear polarization resistance or LPR probes. It is measure electrochemical activity to detect increased corrosion activity that precedes cracking. Monitoring techniques. Number C, hydrogen monitoring. It is to detect hydrogen ingress, which often accompanies SCC, especially in susceptible alloys. Number 5 of the inspection and monitoring methods for detecting ethanol stress corrosion cracking damage is inspection frequency and strategy. Strategy number A is to perform routine inspections, including visual inspections at scheduled intervals, and use NDT methods periodically, especially after stress events or environmental changes. Strategy number B is in-service monitoring, continuous AE or stress monitoring for early crack detection. Strategy number C is targeted inspections, focus on welds, bends, supports, and areas with high residual stresses or corrosive potential. The challenges and best practices for inspection and monitoring methods for detecting ethanol stress corrosion cracking damage includes detecting microcracks, require sensitive methods like ultrasonic, eddy current, or magnetic particle testing. Accessibility, use remote or portable inspection tools for confined or hazardous locations. Surface preparation, proper cleaning and surface smoothing enhance detection accuracy. Data analysis, use advanced data processing and pattern recognition. For early warning. Early detection of ethanol SCC is critical to prevent catastrophic failures. A combination of visual inspections, NDT techniques, and real-time monitoring provides a comprehensive approach. The choice of method depends on the location, accessibility, material, size of cracks, and operational conditions. Thank you.